the line along with the equilibrium, and there's a hypotenuse here. We've got ourselves a right angled triangle. Now, what's this distance here? It's the same as this distance there, same as that distance there. It's A, it's the amplitude. So here's the amplitude, here's the displacement, here's a right angle. Now, this can be thought of as theta. Now that we've got this far, I'm going to rub all of these definitions and things off here. I'm going to draw us a bigger triangle, because what I hope we're seeing is that the circular motion and the simple harmonic motion, or the oscillation, they are linked. They are kind of the same thing. So, let's draw this again. We've got ourselves a triangle. Now, we've got ourselves a triangle. Let's draw it like this. There's a triangle. X, A, amplitude. Now, I was just going to put theta in there, but I want you to be aware of something. In circular motion, back when we did circular motion, we learned a formula involving theta and time. It was angular velocity equals theta, number of angles turned through, per second. So we can quite easily say, instead of putting theta in there, we can say theta equals omega times time. So we're going to put in here omega times time. I hope you can remember from circular motion. So this is theta, but it's also omega t. Now, because this is a right angled triangle, it's not really hard for you to just see that x displacement equals a sine omega t. Omega t must be in brackets because you've got to do the multiplication before you do the trig function. X displacement equals a sine omega t. You have just used circular motion to help you understand what's going on in an oscillation. That is very cool. Physics is pretty good. Okay, what else can we discover? That's fact one. X equals a sine omega t. Not only that, but we can discover that when you think about it, the velocity of an object oscillating is out of phase with its displacement. Now, what am I talking about? Equilibrium position. Battle stations, oscillations begin. When is this thing moving at its fastest? It's as it passes through equilibrium. When its displacement is zero, its velocity is maximum. When is its velocity zero? When it gets to that point. Its displacement is maximum. Out here, displacement is maximum. Velocity drops to zero, and then it starts heading back in the other direction. So you can see to yourself that velocity and displacement are out of phase. How much out of phase? Quarter of a cycle. Quarter of a cycle? 90 degrees. What do you mean 90 degrees? It's not a circle. Oh yes, but it is a circle. Fact one. Simple harmonic motion is related to circular motion. There's always the invisible circle. The invisible circle of physics is always there. You can't see it, but it's always there. It's always there. The invisible circle of physics. Believe it.